Hi, welcome to the Signal Path. This episode begins with my hope of trying to get this PXI card that I picked up from eBay as an as-is unit working in my PXI mainframe. Now, if you remember from my previous video where I showed all my PXI modules, I had just bought an 8-channel Signal Analyzer, which were 24-bit on each channel, but I didn't have any way of generating 24-bit resolution signals as an output. Now what I really wanted was something that can generate output and input so I can do some audio analysis, which is the topic of this video here for some amplifiers that I had bought. But of course I picked this up and I was happy about the price, and when I received it I noticed some imperfections. But first of all, before we get to that, what is this unit? Well, this is a National Instrument PXI-4461, and if you look it up, it has 2 input channels and 2 output channels. It's a dynamic signal analyzer essentially with 24-bit DACs and 24-bit DACs and ADCs, just like the other version that I have, except that one has only inputs. This actually has the output, so we can close the loop and do some analysis. And these guys should have more than 118 dB of dynamic range, which is extraordinary, perfect for testing audio signals, because as far as the signal generation side is concerned, it's almost ideal, these type of things. But anyhow, so I picked it up and I first noticed, and if you look closer you might be able to see it here as well, you can see that there is one capacitor missing, and this capacitor is missing most likely because it has received an impact and the component has been ripped off the board. Then I became suspicious and I looked a little bit more closely, and this is what I saw. Oh, that's too bad. This has been received an impact from this side. You can see all the pins are bent, and it's going to give us definitely some problem if I were to go ahead and plug it in directly into the unit. So luckily I hadn't done that yet, and it's also you can see quite a bit of discoloration here. This has been exposed most likely to moisture and so on, so I'm going to have to find a way to clean it. And of course my cat is here to investigate. Go away, Pooch. And so that's going to be an issue. So I'm going to try and first take it apart so we can clean it. Sorry about the reflection from my spotlight here. And then there's also another issue. This little tab is broken, but I paid very little money for it, so I'm not too worried about it. But we can go ahead and try and see what we can do with it. So let's take it apart, and then I'm gonna figure out what this component that's actually damaged is, remove it, see if the pads are still intact, the traces are intact. This is most likely just a decoupling capacitor, so we should be able to replace it with one of the other ones that looks similar. We can get the value and replace it, and then see what happens. All right, Pooch, do you agree? So here's the result of the unsoldering. You can see I've taken the IC out and I've straightened all of its legs out, and I've taken all the excessive solder off, and this is the pad frame of where it used to be. And you can see that I've lost 1, 2, 3 pads. Now these 2 pads that I've lost I don't think are connected to any traces, and that explains why they came off so easily, because they have so much less structural integrity, because they have nothing to hold them onto the PCB except their own surface. And this one is connected to this trace right here. You can see it's unfortunately been removed, but luckily the traces on the other side are making it much easier to make a connection when the IC is down. Now some of these are actually off the PCB, especially this one is really being held on with by a little thread there. This connection here is quite compromised. I may have to fix that, but I'm gonna dig out and see what this part even is. But putting this IC back there, it's gonna have to receive some kind of extra support, perhaps a drop of super glue there, but that means that taking it off if it doesn't work will be even harder. So maybe I'll solder it on, and then I put seep some super glue under it here and here afterwards if everything is working and coming back to life. So let's take out the data sheet and see what that part actually is. So it turns out the part in question is an IDT quick switch product, which is a high-speed CMOS quadruple bus switch. It's a really straightforward circuit. It's just very high speed. It's got 4 output enablers buffered into 4 NMOS transistors, which then become like a bus switch. So if for example, as an example, let's say you have all of these 4 connected together, by turning these buses on and off, you can select which of them is connected to the output there. So it's a really straightforward circuit, likely connecting some obviously internal bus of this whole PXI module together. Nothing complicated. And if you look at the pad frame, that's much more revealing, and as I suspect, you can see that there is a no connect and a no connect pins there, and those are the 2 pins across the IC which are actually missing. Now if I go ahead and look here, if I orient it in the same direction, which I believe should be like that, there we go. You can see that you probably can't see it all the way over there, but this is the pad that's gone, the top left pad and the bottom right pad corresponding to these two, and the other pad that's gone is this one, pin number 6 2A, which is used for something. I'm not sure exactly what. There is the other type of configuration here, but we are looking at the QSOP package here, which has all the way to 16 pins. That's the one we're dealing with here. So anyhow, you can see that the no connects are not going to give us problem there, but they will reduce, of course, the structural integrity of the whole IC. That's why I was thinking of putting some glue on it. So I'm going to go ahead and put this on there, solder it on. I will not put the glue yet until we plug it back into the instrument, and I'm going to try and replace that capacitor and then go from there. Alright, here we are. Sorry about the mess. I was just working on this, and I went ahead and I put the IC back. There you go. You can kind of see it. And I looked at it under the microscope, and it looks reasonably good. I don't know if it's focusing, but you can kind of see what I've done there, and I replaced that missing component. That was just a capacitor. And I also took the boards apart. If you remember, this was a 2-board construction stacked on top of each other, and this is the back of that board that you couldn't see. It has a Xilinx FPGA on it, as well as some other T. I believe this is I'm not sure exactly. This is the National Instrument part, if I'm not mistaken. I have to take a closer look, but there is a temperature controlled oscillator here, which of course is the main oscillator that is used for all the ADCs and DACs, and that has to be super clean, of course, because we're dealing with 24-bit data converters, and any jitter on that is going to eat into the ENOB, of course. And if you should watch my video on data converters, and there's some more information about that. So I think that looks good. I looked at it under the microscope, and I think that the soldering is reasonable. And this is the other side where the inputs and outputs are actually taken, and you can kind of see what the signal path, no pun intended, looks like. The center pin actually is connected to this pin right here, and the ground is the other one. So they take this as a differential signal, and you can see they turn into a differential signal. We've got 2 inductors and 2 capacitors, part of the matching network perhaps, or flattening the frequency response of these channels. Here are the, let me see, yep, these are the 2 input channels. So just to make sure, yeah, these are the 2 input channels, and these are the 2 output channels. You can see the output signal comes from this, which is a board-to-board connector from the other side, and this is the range switch for the A to D converters, because it has multiple ranges, and it gets processed and filtered and so on, and before it comes out of here and goes back onto this board. So the data converters must be on this board. Anyhow, I'm going to put it back together. I'm eager to put it inside the PXI chassis and see, I'm sure it will get detected. Whether it works or not is a different story, but anyhow, let's try it. There's only one way to find out. Well, while we're at it, let's look at a different PXI module that I've picked up, which is also defective in some way, but I think the problem for this one is not so serious. So this is a 2 bank of microwave switches. Oh, I think I'm zoomed in too much. Here we go. This is a 2 bank of microwave switches, bank A and bank B, and these are simply 1, 2, 3, 4, 5, 6 to 1 switches. So you have a common mode of the input here, and then you can select this to be microwave connected to any of these other ports, 2 independent banks. This is an RF switching bank basically, and they work all the way up to 26.5 gigahertz, so they're pretty high frequency, and these things have remarkable repeatability simply because they are mechanical relays and not solid state. So they're pretty good, and I got this for very little money. And I've been looking for a microwave switch that goes up to high frequencies for some experiments I wanted to do, and this is a good one. Now this one doesn't completely work, and if you take a close look, you can immediately find out why. You can see that this connector has also suffered definitely some mechanical damage. I'm not sure what people are doing with these PXI modules. It seems like they're just tossing them together in a bag and then shaking them vigorously, because they all have some kind of a mechanical damage. Now this connector seems to be in good shape. This connector is obviously not. So what I'll have to do is remove the connector and perhaps perform some surgery on it in order to fix it. And now this obviously is held up by a cable, and this cable will come out, and this way I can just work on the connector by itself. The other thing I can try to do is obviously, of course, compare the circuitry to these two to make sure that all the connections are correct. But the circuit is very simple. At first glance you can see that obviously we have a whole bunch of transistors which will act as switches here in order to turn on the relays that are inside the microwave switch bank over here. So this is nothing more than that. Everything else that you see here, the Altera FPGA, some NI parts, a bunch of memories and so on, these are just simply to communicate with the PXI bus. So this whole section is just the interface to the PXI bus, and this very simple circuitry over here is for the microwave switches. Now you can see that there are other connectors available here, some non-populated components over here, and this is all simply because this board probably is designed to work with different types of switches, with some with more or less number of mechanical components on it. So that's why there is definitely these other components are there. This is the main reason. So let me go ahead and unsolder that, and I'll give you a close look once I remove the connector, and then we'll see if it's repairable. And here's the connector. I've removed it, and you can see that it is in pretty good shape after I cleaned it up. The pins are all there. I should be able to definitely reuse this. I don't need to get another one, so I'm happy about that. But the board itself is a slightly different story. You can see that I've lost quite a few of the pads. This actually did not happen during the unsoldering. This happened when the damage was done initially to it, and those traces were just held in place because the other pins of the connector were still soldered, but they were actually already cut off the board. So you can see that I have lost here 1, 2, 3, 4, 5, 6 of the pins, and all the ones that I've lost seem to have been important, except perhaps this one. And you can see that the traces here and here, especially this one, where there's just a tiny dot of the copper still left and the trace is completely gone. Now, if you take a closer look at this and then figure out exactly how it's connected and how it works, it will make the repair job significantly easier. So this connector here has 10 wires on it. Now, not all the 10 wires are needed because there's only 6 relays inside each of these. In fact, the pinout is written right over here. There's C, which is common, and there's 1, 2, 3, 4, 5, and 6. Each of those driving the coil that is responsible for a specific microwave relay there. So out of the 10 wires, only 7 of them are going to be used. 1 ground, 6 switches. And let's see if that makes sense from what we're looking over here. So out of all of these, you can see the ones that actually are intact are the ones that are unused. So out of the 8, I have 1, 2, and 3, I believe. I'm looking through the camera LCD here, but I believe those are the ones that are not used. Now, if you look at the number of MOS transistors that are here, there's 2, 4, 6, 8, 10, and 12, which makes sense. There's 12 of them, 6 per relay. So each of these individual MOS switches is going to be responsible for driving one of the relays. So if I go ahead and check the connectivity between these cut traces and the drain of these MOSFETs, I should be able to find out which is which, and then I can just bring a little cable over and do a little surgery and connect the connector back. That's probably a better way than trying to reconstruct these traces, because I'm not sure how well I would be able to do that. Maybe I'll do it for the ones that are easy, and just the one that obviously I can no longer do, for example like this one, I might take it a step further and do it the other way that I described. So it depends on the integrity of the lines. I'll have to check. But it is definitely repairable, and if it is functional otherwise and it has no other damage otherwise, it should come back to life. Now, of course, I have no idea what the lifetime of these switches are, meaning I have no idea how many times they've been switched. Now, I know that the software, if this is working, does keep track of the number of actuations these switches go through, because they're rated for a certain number of switches before the repeatability and the insertion loss and so on is no longer up to spec. So we can find out if it works once we put it back and read the number of actuators per switch. That should be pretty interesting. If it's in the tens of thousands or hundreds of thousands, then we're in trouble because it means it's quite old. Nonetheless, I should be able to measure and check its functionality. Now, I'm going to go ahead and do that and show you the result. I also have another PXI module which we may repair, but there's an issue with it. There's a missing component. I may send it back to the manufacturer, the person who sold it to me, because it's actually missing something. So anyhow, if not, I'll find something else, and then we'll have a couple of PXI modules to test once we're done repairing them. Should be pretty interesting to take a look. Here we go. Is that just a very quick repair. Obviously, I used the same connector again and just wired up whatever that was missing, and whatever pad that was completely taken off, I actually routed directly to the MOS switches. So now there's only one other thing to try to do, is to plug into the PXI module and actually test the microwave switches and see if they are working now. So I hope that's okay. I kind of secured it a little bit with tape, but this connector is fairly secure, and if everything is working, then I will just put a little bit of glue on the connector so that it has more structural integrity, because it's not all of these pins are actually on pads anymore. So let's go ahead and let's go actually to the other PXI card, and then we'll test all of them at the same time at the end. And the last thing I want to look at is this NI PXI-4071, which is a 7.5 digit, what they call a FlexDMM multimeter. This is from National Instruments, and it has a 1000 volt range, 3 amp on current range, and it can do 1.8 million samples per second, which is quite a lot. The Keithley 7510 can do 1 million samples per second, of course, but it has many other features, which is besides the point. And this thing actually costs on NI's website, about $3,300. So it's pretty expensive, and I wouldn't necessarily recommend that you would buy this if you wanted a 7.5 digit multimeter. Probably best to buy a bench unit unless you want heavy automation and so on, which the PXI module will offer, and you want, you know, combine this with other modules and so on. But they're supposed to have very good performance. I paid next to nothing for this because it was broken. So anyhow, unfortunately, I started looking at this a little bit, and because I've been recording this over a couple of weeks, I accidentally erased about 5 or 10 minutes of footage, which I was kind of debugging through this. So I'm gonna have to explain this to you again. I seem to keep doing that. But anyhow, nothing major has happened yet, so I can explain to you what my thought process was. So one of the very first things that happened when I received it is I was just looking around, and I noticed that this component right here was missing. So I thought, oh, maybe it's just an unpopulated component. But when I looked at the pads, it didn't look like that this was something that was never populated. So it meant that someone had already started working on this, which is always a bad sign, meaning that they have tried and they couldn't figure out what was wrong with it. So the chances of someone else finding out what's wrong with it is even less now because someone already tried. So anyhow, I went on NI's website and found a high resolution photograph of this, and with a little bit of detective work, I found out what component is supposed to go there. I was lucky that the part number was showing on their photo. It happens to be a memory, as you could probably tell by the footprint that it had. So it was missing one of the memory chips in there, and I thought, oh, I have no idea why they removed it, but let me plug it in anyway onto the PXI module and see what happens. I plug it in, and the whole machine doesn't boot anymore, meaning that when this is inside the PXI chassis, the one that I've shown you before, the whole chassis doesn't boot. Now, if you've ever assembled your own computer, you can kind of guess why that might happen. Obviously, this thing sits on the PCI bus of the whole machine, and if you're doing something the bus that you're not supposed to do, it's a multi-drop bus, you can actually hang the computer and it wouldn't allow it to boot any further. So if you've ever put in a defective card, you know that the machine can hang and nothing can happen. So this was already a very bad sign, meaning that something has gone wrong with this, and when you put it on the PCI bus, the whole machine will stop. So I started going and taking it apart and see what happens, and obviously it's already taken apart, so I'm just going to disassemble it. And if you remove the shield over there, you can see the top of this unit, which has all the analog circuitry which are connected to the front connectors here. They're all revealed over here, and you can see that the back of this has some places for individual connectors to make contact to create further shielding. Obviously, like I said before, NI really knows what they're doing when it comes to making compact instruments. So if you go ahead and separate this, we notice that it's obviously a 2-bolt construction. And if I flip it over, you can see all the wonderful typical things you would expect to see in a 7.5 digit multimeter. It's just amazing how compact this is. Here's our voltage reference protected by this case here, some spark gaps here, the fuses here, a couple of relays, and you can see cutouts in the PCB in certain places where there's critical for leakage or protection and so on. You can see exposed traces over here as we have seen before, and you can see, if this would focus, our precision resistors, which are quite amazing. You can see small traces on there. I'm not sure how well it will show up, but anyhow, everything really nicely laid out. Now, the fact that the chances that this would be causing a problem is very, very small, because these are completely isolated from the PCI Express bus, so we have to dig a little bit deeper. So let's put that aside, and here's the top of that board, and here's the missing component. And if you pay close attention, you can kind of tell what the architecture is. You have a FPGA here, you then have the Shark analog devices processor here. This is a DSP processor, obviously to handle all the data that's coming from the analog to digital converters of the PXI module here, to process them all and then handle them and do computation on them before handing it off to the PC. Now this portion where the connector is connecting to the top board is completely isolated from this portion through this transformer. So there's a flyback transformer DC-DC converter here which provides power to this entire half of the board and also powers the other board that I was just showing you. So there's a complete break in the PCB here. In all the layers, you can see right through it if you put it in front of a light. There's nothing there except some optocouplers and the DC-DC converter. So obviously, this is obviously for protection, for isolation, for noise, a whole bunch of things. If there's something ever happens and you have 1,000 volts on your analog inputs, you don't want that to jump onto the PCI Express and either cause potentially dangerous situations or destroy everything else. So nonetheless, we can see that how this works. Now, I happen to trace the DC-DC converter lines here, and the transistors that drive the DC-DC converter are on the other side. So let's go on the other side and take a look. Now, if you look quite carefully, you see a row of resistors here, and this row of resistors, classic sign that something is sitting on a bus. Now, this component is missing, and the reason it's missing is because I removed it, and that's part of the footage that you missed. So if this thing is put inside the computer, and you can see all these resistors here, which are the PCI bus, indicative of being on the bus, all these lines go into this component in here, and that component was this guy. This was an NI branded component. I couldn't find any data sheet on it, but you can tell what it does because it's most likely the PCI bus IC. This is the IC that interfaces with the main bus on the PXI module, and that is where the problem is. If this IC is bad and it causes a short or some unusual state on the PCI bus, obviously the machine is not going to boot, and this is in fact exactly what was happening. When I remove this and then I put this inside the unit, the machine boots. Of course it doesn't get recognized because there's nothing sitting on the bus, there's no communication, so it becomes invisible to the machine. But everything else is still connected, meaning that by removing this, the problem went away. So hopefully this was the problem, and of course by removing it you destroy all the balls because this is supposed to be reflowed and so on. I happened to find a replacement of these in China, and I ordered them. They're supposed to arrive on Monday, and which is a couple of days from now, and I'm going to try and resolder this back. This has been a huge hassle, and if this wasn't such an expensive module, I would have just given up on it, and there's no guarantee that the new ones that I get are going to fix it, but it is worth a try. It's going to be also interesting to try and resolder this by a hot air gun and so on. That'll be fun. Another thing I noticed is that these are the transistors that run the DC-DC flyback converter, and they're actually driven also by this IC here. So this IC controls not just some of the functionality over here with the memory and so on, as well as communicating with the PCI bus. It also controls the powering on and off of everything that's on this half of the board. So it makes sense that nothing was happening. So this is kind of where I stand right now. I have ordered a replacement part for this. I already have it. I have ordered a replacement part for that. It's going to arrive in a couple of days, and then we're going to solder everything back together and see what happens. And if it comes back to life, that would be a pretty awesome repair. And if it doesn't, it was still a very interesting learning experience because I managed to kind of do a little bit of reverse engineering on this and figuring out exactly what is happening. And some of these components might become useful in the future. So I'm going to wait, and I'm going to come back again and record this once I receive the components. I hope you caught up to what I was doing so far, so you didn't really miss much. So let's see what happens next. Alright, here we are. Some time has passed, and I actually managed to find a replacement IC, and I ordered 2 of these, and it arrived in this waffle pack. Actually, there's only 2 in here, of course. It cost me about $50, and these are BGAs, of course, and they are going to be, I'm going to try and solder them back on. And I removed the old one, as you saw before. Some of the pads have come off, the BGA footprint there on the PCB, but when I look at it really closely, I think that they are probably connected to nothing, which is why they came off easily, because there is no structural integrity on them. There's no wire connected to them, there's no via. So I'm going to try and align one of them. I already put some solder paste under, and I have this little rig here where I have my hot air gun over there that's going to be pointing directly down on there. I'll hopefully provide a nice clean stream of hot air there to bring the temperature up, and then hopefully it will reflow in place. It's a long shot. Of course, this is a pretty dense BGA package, so it's going to be difficult to try, but it's difficult to do it when the camera is in the way, so I'm going to have to unfortunately put the camera on the side, but I'll try and see if I can film at least before I start, and then we'll see what happens. And either it comes to life or it doesn't. Either way, it was a good experience. Alright, here we go. It's aligned, and you can see here, and I've done the best I can, and it's all protected by tape around, of course, thermal tape to make sure that the other components don't come off. And I'm gonna turn the temperature on and slowly raise it, allow the board to expand naturally, and try my best to kind of follow the profile that normally you would have for a reflow. I don't want to put the whole board inside an oven because he has connectors, he has a whole bunch of other things, it's populated on both sides, and I want to make sure that nothing kind of gets even further damaged. So, well, wish me luck. I'm going to turn it on, and I'll show you what happens afterwards. Alright, and we are in the cool down process right now, so I'm already lowering the temperature. You can see it's at about 100 degrees Celsius, so it's come down quite a bit, and I think it refloat before, just like I've done BGAs before, and this one behaved exactly the same as I would have expected. So seems okay. I think it's got soldered correctly. Whether this was the only problem or whether this would solve it is a totally different story. But I think the soldering was successful, and I also soldered the missing memory on the other side, which actually looked very, very similar to the component that's right here in the corner of the screen. And it's pretty straightforward, of course, and so I didn't really show that. But so now that I'm going to wait for it to cool down a little bit more, and then now we have three different cards, and I'm going to put them in the PXI module. And if the PXI module boots at least, then that's a good start. Alright, I went ahead and I put all the PXI modules in the system. Unfortunately, the multimeter, which is right here, still locks up the system, even though I replaced the IC that was on the bus. So I'm not sure exactly what's wrong with it anymore, but I really want to get this video up, so I'm not going to fiddle around with it anymore, or not right now at least. I'll look at it again later. I walk you through my thought process, so I'd love to hear what you guys think. If you have any other ideas that I can try. Either way, without that BGA package, it certainly boots up, and with it, it doesn't. So there's something going on there. We can think about it. We can take a look at it later. I really want to get the video up and show you guys what's going on, and also have a bunch of other things to repair and a whole bunch of things to review. So I really want to get things going. So let's start with looking at the microwave switch here. So this is obviously the module here on the left. The bottom microwave switch was the one that was had the problem with the cable that I replaced and the connector that I fixed. So I've connected it up to a bunch of different instruments. The input common to the switch is coming from a synthesizer, and all the outputs are going to different instruments. The first 4 outputs go on to my Keysight oscilloscope, so we can see if there is any signal coming out. Right now there is nothing. All the 4 channels are enabled. The 5th channel goes on to the Agilent spectrum analyzer, and the last channel goes on to my Rigol oscilloscope here with my cat. Yeah, I gotta get his tail out of the way later. But anyway, so there's nothing going on right now, and the synthesizer is just a tracking generator at the bottom set to 100 megahertz. Obviously, I'm not measuring the frequency response. That has to be done later. I just want to make sure the switches are alive and have at least a flat response at 100 megahertz. In order for you to really truly check them, you need a network analyzer up to 26.5 gigahertz, and then you can check it very carefully like that. But for our purposes right now, it's fine. Then I have gone ahead and loaded the NI switch software, which is over here. And there's a bit of a glare in there. Let me see if I can get rid of that. And you can see that that software over there allows me to control all the switches. So this is the bank number 1 over here. And if I go over here, you can see that the lifetime of the switch is actually listed and how many actuations they've had. And look, they're all less than 100. Only the first one is 118, which is nothing. This is basically completely brand new, which is fantastic, which means these switches have a long, long life left in them. Now if I go over here, I can individually turn them on and off, and you can actually hear the relays click from the camera, along of course with my mouse that's been clicking. So let's go ahead and disable all the switches, so now none of them are closed. And if I go on over here to the Keysight scope here and get this out of the way, let's go ahead and enable channel 1. Let me go and trigger on channel 1 and check it out. No problem. Here's channel 1 coming out. I can go to channel 2 and I have to trigger on channel 2. Perfect. Channel 3, trigger on 3, no problem. Channel 4, trigger on 4, no issue at all. Then we go to the spectrum analyzer over here, enable channel 5. There's our signal. And finally, we go to the other oscilloscope and enable channel 6. No problem. Works perfectly fine. And yeah, that's great, Bush. Thank you for your contribution here. So it looks fine. It works perfectly fine. I'm pretty happy with it. I also tested the other microwave channel in a similar way. Obviously, it works perfectly fine too. It's basically brand new, and this repair saves this PXI card and brings it back to life, which is fantastic. So again, I can do more detailed tests later. This will definitely verify that it is good, up and running for now. Now the other one was of course this dynamic signal analyzer with the output and the input, and we can go ahead and try and see if that one's back to life as well, and see if we can generate some tones out of it. And to test the dynamic signal analyzer, I've just connected both of its outputs directly onto the oscilloscope on channel 1 and 3 of the scope. And I have written some MATLAB code, which is pretty straightforward really. It just generates an array for a sinusoid and then uploads it to the PXI module itself, and then it takes care of all the timing and everything internally. If you've ever used the drivers for data acquisition from NI and the MATLAB toolbox, you would have seen something like this before. And maybe if there is interest, we can go into the details in a different video. But just wanted to see if it's working. So I have channel 0 enabled here, so I'm gonna download my waveform. It takes about a second or two for the driver to actually initialize from the PXI mainframe. It's not the fastest computer in the world, and check it out, here it is. It looks great. A nice sinusoid, plus or minus 1 volt, 5 kilohertz without any problems, and it's quite linear actually. The waveform just ran out. I was downloading it for a certain duration only, and it works perfectly fine. And I tried the other channel, and we can try that as well. But there's actually a software built into the machine itself that has a little soft panel that can communicate with the module, and there we can even generate and receive waveforms at the same time with it, so I don't have to write some more code. So let's go ahead and launch that to make sure all the channels are working. And here's the soft control panel for this specific module that I have, the PXI module, and you can see on the left here all of my other PXI modules here listed. But anyhow, this is the one that we're interested in. I have it here set to channel A0 of the input, and if I go ahead and start acquisition, of course it's gonna show nothing because there is nothing connected. But I have created a loopback. I've connected the output of channel 0 to the input of channel 0, so I can go under the analog output, select channel 0 here, and generate a sinusoid. Like so. Now if I go back, you can see that I'm actually capturing the sinusoid that I'm generating myself. So the whole thing works. It works in loopback. I can do it in both channels, channel 0 and channel 1. So the whole dynamic signal analyzer seems to be working quite nicely, and you can here see my little loopback. So I would say that's also a successful repair. Of course, I have to do more details, make sure that the THD works. I did a very quick test with the THD on my spectrum analyzer, and the THD is above 80 dB, minus 80 dB, so it's pretty amazing actually. So it's going to be no problem at all with the kind of stuff that I'm interested in doing. And unfortunately, I couldn't get this thing to work on this run, but I would love to hear what you guys think. I'm sure that if we put all our brains together, we can find out a way to fix it. So if you want more information or pictures of it and so on, I can try and post it on the website to try and debug it. But as I said, I have replaced the IC, and it still locks up the device. So let's think about that and go forward. Just wanted to put a quick video. I have a network analyzer that I'm repairing that I want to put. There's some interesting high voltage power supply that I'm also working on. There's a couple of reviews, so there's a lot coming. Just been very busy lately. So I hope you like this quick video update, and let me know what you guys think, and I'll see you soon.